I think let's get started. So we'll do I hope you guys can see my screen. So we'll do a brief recap of what we had seen yesterday. So basically what we did yesterday was we had taken an program and we were looking at how GPT or LLMs would answer it for us. Basically, we had taken a buggy code where total is equal to price was there, but we wanted the sum to be printed, the total price to be printed. So we asked a question that what is the bug in this particular code. Then we looked at tokenization, which was just converting them into the numbers. We looked at the table, which helps in converting them into a number. We looked at vectorization, which basically means is like mapping the tokens to a vector. Vectors, we saw how the vectors capture the meaning of the words. Then we looked at positional encoding. Positional encoding, basically what it means is like in a sentence, we also need to look at the positions of the various words because they also matter in order to understand the contextual meaning of the sentence, right? To generate to the generated vector on the third step, we added positional encoding so that because positions also really matter. Then we looked at attention, right? So this is the most important part. What happens over here is each word in a sentence looks around different words so that a semantic meaning or an understanding of the sentence comes, right? So that it absorbs the meaning from its surrounding context. We looked at that. Then we looked at feed-forward neural network. The output of attention is passed to the feed-forward neural networks. What are feed-forward neural networks? We just saw that they are pattern detectors, right? We have the absorbed context from the surrounding vectors. Each word has the vector which has absorbed the context from surrounding vectors, but we via these pattern detectors, we want to sharpen the signals and whatever is not relevant, we want to adjust the vector accordingly. So we also looked at what does the feed-forward neural network do, right? So after these steps, right, these 5 steps are also the steps that an LLM does. After these 5 steps, model now has understanding of the code and the bug, right? So our code was this, and there was a bug in the code. So the model now has an understanding of what we are talking about and what is the bug in the code as well. And we saw step by step how it can understand all the words and then the context around all of this, right? So now the next step that the model has to take is, hey, I understand the code. I understand the bug that you are talking in the code that you pasted. Now the model has to answer back, right? So that's the only step remaining. I have understood the context, and now I need to answer back. So now what the model will do is we have the last vector in the sequence, right? Which was our code, then the question mark, right? The one sitting at the position of question mark. This is the vector actually which matters the most. Why? Because this is the last vector in the question and it has absorbed all the meaning from the previous context. It knows about the code that we are talking about, the bug in the code. It understood that there is a bug in the code via attention and feed-forward network, and it also has an understanding of our question about it. So basically what I'm trying to say is, so what did we do? We had this price thing. We had this program total is equal to 0 for price in prices, total is equal to price, print total, right? And then we posted a question, why does this print the last price and not the total price, right? This was our input to the LLM, right? And we want an answer from the LLM. We are looking at the inference phase of the LLM. That is what we look. So now this vector, right? As I said, each word in the sentence will be broken into individual words, and then vectorization, tokenization, everything happens, right? And a semantic understanding is developed, right? So this question mark, which is the last word in the sentence, our input, right? So this sentence, what will have is it will have all the contextual information absorbed from this line. Okay, the lines above it, which is this whole program, this for loop, and the lines above it, these lines also. Okay, so it will have all the information. This question mark will understand everything. Okay, so basically what has happened is like we had split our program like the individual sentence into words, right? Each of the words. After vectorization, we had seen that each of these words had a general meaning encoded within them via vectors. We saw that very clearly how the general meaning is encoded. For the question mark, similarly, had a vector for it, and it had the general meaning of the question mark. Now, each of these words, right, in our question or in our sentence, goes through this some transformation layer. We talked about this transformation, which is tokenization, vectorization, attention, and feed-forward neural network. Now, each of these words, right, via attention or this transformation mechanism, their vectors got modified. Like the vector of total got modified into from 1 to 3 to 5, 7, 6. What does it mean? Is like the vector of total after all this process has grabbed the contextual meaning of what it's doing over here in this context, right? So that has what has happened. Similarly, like every other words vector has changed. Okay. Now the vector of this question mark also has changed in a way that it has context. Initially, it was just a question mark vector, but now it has absorbed context from all of the things above over from here, right? And this the modified vector has the understanding of the code, the bug in the bug in the code, as well as our question. So this is what this line means over here. Okay, that the question mark vector has absorbed all the question, and now it has understanding about the code, the bug, and the question about it. And we saw, right, we apply multiple layers of attention plus feed forward network. And like I told you yesterday, right, there are 96 layers in total, right? The LLMs have a total of 96 layers of attention via which it understands everything. So what has happened in each layer for the vector question mark, for the vector of question mark is, initially, let's say the vector was like this. So it has just this simple understanding that question mark is just a question mark at the end of a sentence. Then it went through transformations, and in the middle layer, it understood the user asked a question about a Python bug, right? And then after the 96th layer, or maybe whatever layers are present in the transformer, it will have an understanding. The answer should explain the accumulator bug on line 3, right? So question mark now has all the understanding, and like we saw that now the model understands the code, the bug, and the question about it. Now the model has to answer, right? So now in the final step, what the model will do is, you remember that we talked about an embedding table in the vectorization step, right? Which I told you that there is a table which has all the English words in it, and all the English words are mapped to a vector, right? And from there, the vectors are picked up, right? So now the model will, what it will do is, now it will do that the reverse thing. The final vector, which is the question mark, it will take that vector and do a comparison against the same embedding table. The comparison is a dot product because it measures similarity. Okay, what do I mean about this is, so I have the final vector of question mark, right? Which can be something like this. Okay, some number, some vector. So I said we have a table in the first, when we were discussing about vectorization, we told that there is a table which has all the English words mapped, and all the English words are mapped towards a vector which somehow encode the meaning of the English word, right? So now what will happen in the final step is, we will take this vector of this question mark and do a dot product against each entry, okay, in the table. Against, like if it has 5,000 entries, we'll do a dot product against all the 5,000 entries in the table, okay? And what did I say? We'll do a similarity search, or we'll do a dot product. So what does dot product over here means is, like, let's say if you have two vectors, right? Vector A and vector B, if you do a dot product, it tells you the angle between these two vectors. If the angle is less, means both the vectors are similar, right? If the angle is more, it means that both the vectors are far apart. And what we have understood so far is, like, similar vectors live in the similar space, right? So that is what we have seen already, like cat, dog, they will live in the similar vector space. So if they are similar, the angle between them is very less. If they are far apart, or if they are dissimilar in meaning, then the angle between them is like is too large, okay? So what I'm saying is, we'll take the vector of question mark and do a dot product with all the entries in that table, right? So now what this will happen is, what this will help me in doing is, it will help me in predicting the next sentence, right? So going back to our example, the first examples that I used to give, the sky is right, and then it has to predict the next sentence in it. So think of it like, we have this is which has absorbed the context from sky and now I am taking is and doing a dot product over here. Now what will happen is, blue will be closest to the vector of is, right, on similarity lines. So something like this will happen, and now it will predict the next word to be blue. Okay. So this is what we are telling over here. In the last step, the vector of question mark will be taken. It will be compared. A dot product will be done with all the English words, and then the closest will be chosen, right? So when we do the dot product with the 50,000 numbers that are a part of the table, they are technically called logits. Okay. They are the raw similarity scores. It picks up the best match. Like again, coming back, like what will dot product will give us is these angles, right? So it will give us the probability that, okay, hey, okay, the word the is like 10% close, or like it's like similar 10%. Maybe the word bug is like 50% close. So it will try to find the best match that should come after this question mark. Okay. So how will the question to our question, how does the LLM respond? The bug is on the line 3, right? So after the question mark, it will figure out the is the best word that comes after it. Okay. By doing a dot product in the embeddings table. Now it will take the whole input and take the word as well, and then predict the next word. Then it will see based on the context. Okay. The context of the code and everything has come over here. Now it will predict bug is the closest thing. Then so on and so forth. It will keep on doing this, and we will get an answer like this. The bug is on the line 3. Right? So how it will predict this answer, we got it, right? After our question, the question mark had all the context absorbed from the surrounding. It had understanding. We did a dot product from the embeddings table and started predicting the next word in the sentence, right? So this is how we'll get the answer. Okay. So this was the end-to-end scenario, how an LLM answers your question. So just a recap, the complete picture from the feed-forward neural network to the next token is the last feed-forward neural network produces the final vector, which is the question mark. Take the last vector, question mark, compare the V final against every word in the embedding table. We take a dot product. How similar is my understanding to each word? Then it gives a 50,000 raw scores because we have compared it against all the rows in the embedding table. These are called logits, like I said. Pick one word which is the closest by greedy method or by sampling. Then append that to the input and run the whole pipeline again till you give this whole answer. Okay. So this was our overall flow, which is like perfectly explained over here. Like I said, what did we do? We had this input question. We converted them into vectors through tokenization. When we were doing vectorization, it had the general meaning of each of these words. Then it went through a transformation layer wherein we did attention and feed forward network, where it looked at the surrounding words and understood what is going on in our particular sentence. And then what happened is all the vectors got modified. It had contextual information. The final vector of question mark had all the context of the bug, the code, and whatever the user asked is. We multiplied it. We took the embeddings table and saw what is closest or the next nearest thing which should come after this. We took that, repeated on, and this is how we will get the answer for it, right? This is how end-to-end workflow works for an LLM. Okay. So what are the steps? Our input sentence or the question that the user has. Then what is the next step, which is tokenization. We saw that this is converting into number. Okay. Then we had vectorization, which is like encapsulating the semantic meaning or the general meaning of words. Then we had attention, which is like looking around all the words in the sentence and then updating their vectors so that the surrounding context meaning is absorbed. Then we had feed forward neural network. Okay, so this strengthened the signal. It had patterns. It detected more patterns and helped in figure out what the exact bug was. So it helped in strengthening the signals by expanding the vector space and then contracting it, right? And then there was a prediction layer which took where what we did was we took the last vector which had all the context, compared it against the table, and then started our prediction that what word should come next, because we had all the context. So this is how the whole LLM works. This is the workflow. Now, yesterday, what I had told, right? This is and the inference workflow. Okay. So a model has two parts, right? What I also talked about this yesterday briefly. The model has two parts. First, the model has to be trained. Once the model is trained, then it can answer the user questions, right? Now, for these LLMs or chat GPTs, the training happens on millions of data on the internet, the whole of internet, basically, right? All the articles, everything which is present on the internet, they are trained on all of that, okay? And when the model is ready, then it can predict answers, right? And during the training, what happens is it learns the relationship between the data, right? And during inference, it has already learned the relationship. Now it can answer based on its training, okay? It's very similar to what, like when we say it learns the relationship, right? You can keep the same analogy in the mind that you had given X and Y, like X and Y were the input to the model, right? In our neural network example, which was like 1 is 3, 2 gives the value 5, 3 gives the value 7, right? So this is our training data, right? So during training, what did the model learn? What is the relationship between X and Y, which would be Y is equal to AX plus B. And it also learns what is the value of A and the value of B, which will help me answering what is the value of Y for X is equal to 5. So it can learn that also. So this phase is called the training phase of the model, right? Now, once it has learned all those things, it can do the inference. Inference means giving answers to the users. Okay. So now, like I said, right, now coming back, so we already discussed the inference phase, like how will it give answers? Now let's focus a little bit also on this part, like what happens during the training of the model. Both are similar, but there is just just a slight difference. Okay. So like I said, right, during the training, uh, it understands it's trained on all the articles present on the internet, right? So basically, like I said, right, these LLMs are, I don't know, I had this misconception when I started working on LLMs, like they are searching on the internet, okay? But actually they are not doing any search. Like lately, there have been some developments where the model can do search also, but during the training phase, right, you might go to GPT or some other like Claude and everything, and you will see over there that during the training phase, right, they say that there is a cutoff date. So the model is trained till this date only. For, let's say, if you take like GPT 5.5, right, so it will have a training cutoff date, which is like it has been trained till January 2026 data only. What does it mean? Whatever was present till January 2026 on the internet, I have trained the model only until this data, right? So what I'm trying to convey over here is it is trained on the internet data and then it can answer. So in the training phase, what happens is there is a concept called self-supervised learning. Okay. What is self-supervised learning? Okay. Let's say there is an article on the internet which says the cat sat on the mat, right? Now, during self-supervised learning, what happens is the model will mask the last word in the sentence, which is like, let's say if my sentence was the cat sat on the mat, I will mask the mat part. Okay. And now I will tell the model, hey, predict what is the last word in this sentence. Okay. So now what model will do is model will initially predict wrong, right? Because I'm talking about the training phase right now, right? So the model will say the cat sat on the table. Okay. But table is wrong because we know we have provided this input already and masked this part over here, right? Before masking, I know over here it should have been mat, right? Now the model, because it was untrained at during this part of the training, it predicted just table. So now what I know, mat is not equal to table. So what I will do is I will calculate the loss. Now go back again to our neural network example where we had X and Y. And initially, what after knowing that the relationship between X and Y, what we had done is we were taking the value of a1 and b1 and then trying to predict the value of y dash, right? If I substitute a1 and b1 over here, what I was getting 2. So I know the actual output should have been 3, but I saw 2. So I know that the loss was 1, right? Again, I substituted this value in x and y and a1 and b1, and I saw that the predicted output was 4, but actual should have been 5. So I computed the loss and went back and updated my a and b values, right? This is what we were doing during the neural network class. This we call back propagation, right? And this is also what is called learning of the model. It learns what should be the parameters a and b, right? So we know that it was going back and updating the parameters a and b so that it can have an understanding, so that it understands the context, right? Similarly, what will happen over here, right? So now when the LLMs are trained, right, we looked at the inference phase, but what happens during the training phase? Okay, same thing happens. You pass the input sentence, but masked, right? You masked because we are doing training, right? So we are passing the trained data where we know already the answer. So the input will be masked, like I explained over here, right? I know that this is the sentence, but I will on purpose mask this mat part and I will tell it complete this sentence, right? So same thing will happen over here. I have masked my input. Then the tokenization phase, which we talked about, will happen. The embeddings, which we talked about, will still happen. The positional encoding will also happen. Attention mechanism will also happen as it is. We'll pass the output to the feed forward neural network also, same that we did during the inference. Then the prediction layer also happens. But there is one more step which happens during the prediction layer, which is what will happen is the model will see whether based on my input, since I already know the answer of the input, whether the model is predicting wrong or the model is predicting right, right? So if the model has predicted right thing, I will not do anything. Okay. If the model has predicted wrong, then what I will do is there are certain parameters in each of this phase, right? Embedding phase, there are certain parameters. Positional encoding, some parameters are there. Attention phase has some parameters. Feed forward network has some parameters. Similar to our example, y is equal to ax plus b. These were our parameters, a and b. So in each of these phases, there are some parameters a and b, right? And like I said, there are 30, like in a general model, there are close to like 15 billion parameters. in different phases of the LLM. So now what will happen during the training phase, when it sees that the output is wrong, it will go and update the parameters of feed forward neural network. Parameters are also called weights. So it will go to the attention layer and update the weights of the attention layer. It will go to the positional encoding layer, and whatever were the variables or the params over there, it will update them. It will go to the embedding layer, and whatever was the learning phase, or whatever was had to be learned, it will update over there. Just keep in mind the same example. That is why I was saying this neural network part is so important, because you can draw a mental map that in predicting the relationship between x and y in this particular example, we went back, we took different values of a and b, and we saw that, hey, whether this equation is getting satisfied or not. Okay, and then updated a and b accordingly. Similarly, over here, it takes a sentence, predicts the next word, and if the next word is wrong, I know that my model does not have a complete understanding of it, and I will go and update the parameters in the various layers of the transformer. So this is the architecture of the transformer or the LLM. And we also talked about what happens during the training phase. In the training phase, the weights are frozen. Okay, once the model has learned, right, these parameters are frozen. Just again, coming back to this example, after the training, what we know is we had finalized on a is equal to b, a is equal to 2, and b is equal to 1, right? We got this. Similarly, after training, all these weights will be frozen, because the loss would have been minimized, and we know that, okay, a and b are this only, right? So this is called the training phase, where the parameters will keep on changing until the model thinks, okay, the loss now on my training data is minimal. So I have an understanding. I know now I am behaving correctly. I have learned all the relationship which are present based on my training data. Now, if a user gives me new data, I can predict the answer. Okay. So that is training. Once it is trained, then you give it to the users like us, and then we will use it to give us answers. Okay. So is the end-to-end workflow clear over here? Like, this is what today you have understood how LLMs work end-to-end, what is training, what is inference. Okay.
Ankit, I have a question.
Yeah.
While training this, is there any parent module that we can extend and train the basic things and then train it in our advanced level?
So if I correctly understand your question, Swati, over here is like you are trying to say is like, let's say if you have a base model, right? And
Yeah.
you want to train it on your data, your company data, right? Is that possible?
Yes.
Yeah,
Yes. Yes.
it's possible. So what basically we'll be covering in the next class is we had looked into LLMs, right? So LLMs have two parts. One is LLMs are large language models, but we also have something called as SLM, okay, which is small language models.
Okay.
What happens over there is generally these large language models have huge number of parameters, right? So only big companies like Google and all, they can take these large language models because they have created them and train them on the whole of the data on the internet. But for our company use cases, we don't need that much big of a model because our data set is very small, right? So we take small language models which have smaller number of parameters, which require less GPUs, which we can afford and which our company can afford, and then we can train it based on that. So our next example, in our next class, I will take exactly the same example. I will take an SLM and I will train it on my data, and I will show you how how can we get output based on our data, not the data from the internet. Okay. Does that answer your question?
So this answered my question, but I have one more
Yeah.
question. Like, if for ChatGPT, for Claude, and for Copilot, they
Mhm.
have one base model that they are using, and they have
Mhm.
implemented their own changes. Is that
Yeah.
correct?
Yeah, correct. So no, see, a base model is so let me tell you, there are two examples over here. So what happens if I am understanding it correctly? Your question is like, what happens is like I have data on the internet. Okay. Now, what is the general process? Okay. So I have a model. Okay. Now, once I train the model, I told you how the training will happen. After the initial training, okay, there is a version of the model which comes up, which is called the base model. Okay.
Okay.
This is called the base model. Okay. Then what we do is we take this base model and we train it on question answer sets. Okay. Or what we do is we involve some humans where we do reinforcement learning with human feedback, RLHF. Okay. Now the model can answer questions in the format of like sentences like we do. The base model can just do the prediction of the next word, like I said, right? In initial phases, I told that what happens in the next, what the model can do is it can predict the next word in your sentence, right? So after the initial training, when the base model is ready, it can just predict the next word in the sentence. Then we do some more training over here. And then what it can do is, this is the final model, which can answer in the format of Q&A. You pass in a question, you give the, and the model gives you an answer. So this is the final model. Okay. This is the general workflow of any model. Now, what exactly is the question? Like you are telling that Claude or like Copilot or any other, these big companies, they follow this whole end-to-end architecture, and they give you this, okay, the final model, which has also been trained on Q&A and RLHF. Okay.
Yeah, so they all don't commonly extend something. They have their own base models.
Yeah. Oh, yeah. That, if that was your question, they don't extend something common. They build their base models, because I'll tell you what is the difference. Okay, which will become very, very clear. Now, let's say Google, right? Google as a search engine has access to everything on the internet. Mostly whatever is not restricted at a company level, it will have access to, right?
Yeah.
To crawl and everything. So Google has maybe access to, like, let's say 1,000 TB of data, right? Now, Anthropic or Claude is another company that does not have access to this 1,000 TB of data, right? It might do some web scraping, and it can, like Google may decide that I will not give you access to all of this data, right? Because I have scraped the whole internet and I have this data, but Anthropic might have only access to like 500 GB of the data, right? So now when Google will create a model, it will be trained on 100 TB of data. When Anthropic will create a model or Microsoft will create a base model, it will only be trained on 500 GB of data. So their base model can also differ, right? Does this make sense? Is it making it clear how this model will be trained? Okay.
Got it.
This is what will happen, right? The base model of different companies also differ. Okay. Okay. So this is the overall picture, how an LLM works end to end, and what is base model, what is the final model, and everything. Okay. Now, like I said, right, every model has certain parameters. So I will just give you some examples so that you understand. I mean, parameters I have already explained. Simply, y is equal to ax plus b, a and b are parameters. So every model, think like GP2 when it came, it has 1.5 millions of these parameters like a and b, which is like 3 GB of file. Okay. GPT-3 had 175 billion parameters like a and b, which was 350 GB of file. GPT-4 had 1.8 trillion parameters, which was like 2 TB of file. Now you understand, right? How we we are always in wow. How can I give any question and it answers my question, right? You initially, when LLMs came, you might have this thought, right? How is it even actual to answer anything that I am giving, right? Look at the parameters that it's trained on. It's so huge. It can understand all the relationships in the world. Okay, so that is how it can answer anything based on the training data. Okay. And now what is the training data, right? This was parameters, like the number of parameters that the model had. Now coming back to the training data, like GPT-2 was trained on 40 GB of facts or text file, right? GPT-3 was trained on 570 GB of text data. GPT-4 was trained on 10 TB of text data, right? You can see how the training of the data is also changing, right? What is happening is, how are the models becoming smarter day by day? Is like their training data is increasing. Our compute power is increasing. That is why I can train on 10 TB of data. If my compute or like chips were not that much advanced, then I cannot train also, right? The computer or the cloud instances or the GPUs that we are using, they will shut down, right? Because we saw that the level of processing at each level is so high, and we are doing so much mathematical processing over here. If we don't have the compute, the model cannot be trained. And if the model cannot be trained on more data, it cannot answer the questions very efficiently, right? So this is the overall crux of the model end to end. Now, I want to focus on one more thing, is like during the attention, I only told you that the model can look around the words which are around it and grab the context of the words. Okay. But it cannot be in the air, right? I mean, how does it do it mathematically? That is what we have attention. Attention is done via QKV matrices. Okay. And this is not very important to understand, but why I am covering this is, this is your first interview question or the second like if you go for an AI engineer role, this will be your first or second interview question, that how does attention work? Okay. So first, and this is the formula. I will explain all of this line by line, or like how is the internal mechanism happening, what is attention, and how are they translating into this particular formula. But let's look at like what we understood. Okay. So in plain English, how did we understand attention is, first, after vectorization, each word starts knowing only its dictionary meaning, like the general meaning that the word has. Like total is a sum, right? It's not a Python variable. So it just has a general dictionary meaning. Then each word looks at the words before it and ask which of you matter to me, right? So that I can understanding what am I doing in this context. It then pulls in a little bit of meaning from each one, more from the important ones and less from the word. So in a sentence, it will look around all the words. It will see that some words are more important to me, some words are less important to me. So let me grab the meaning from my surrounding context. Now the word knows not just about itself but the story around it, so it understands all the context. This all of these things happens in the attention layer. The last word ends up holding the meaning of the whole sentence, right? Like in our question mark, we saw how this will hold the whole of the meaning of the word, and that words the model uses to guess the next word, right? We are clear on this part. We have seen it end to end. Now what I'm saying is, like, let's say this is our sentence: the cat sat on the mat. So what will cat do? It will look around. Hey, what am I doing over here in this cat, in this context, right? So cat generally means an animal, but to answer or to grab the context in this sentence, I need to look around. So cat will look around into the different words around. Sat is an important word. Mat is an important word. Similarly, sat will do attention and it will look around that, hey, who is doing the sitting action over here, right? I don't know. I just know sat means sitting, right? But what do I mean in this sentence? I don't know, right? So if we look at cat and mat, then it can understand, okay, a cat is sitting on a mat, right? So sat is just a sitting action. I don't know who is sitting on what, right? So it can look around the words and then understand. Similarly, mat is just an object where people can, where an object, where something can sit. So who is sitting? Cat is sitting. How will it know? It will look around the whole of these things, right? So, so we know. So now let's see mathematically what happens end to end. After the embedding and positional encoding, let's say we have three vectors. Like I am taking a very small example that each word is represented just by four dimensions, and this is the vector for each word. In real LLMs, this whole array kind of structure which you are seeing, it will be of 4096 numbers. Okay, this is very huge, but just to make the calculation easier, I am just taking 4 dimensions for now. Okay, so cat will be represented like, for after embedding and positional encoding, cat is represented like this, the is represented like this, cat is represented like this, sat is represented like this. Just a very basic simple example I am taking, so to explain you how attention will work. Okay, now I have this after embeddings and positional encoding. So these vectors are produced after embedding and positional embedding. Let's say this is the word. Now, what will happen next, right? So during the attention, what happens is each word plays three different roles. Okay, I said we use QKV matrices, right? So it's related to that only. Every word, focus on this, every word plays this three different roles. With every word, what will it do? First thing is, it will ask a question, which is the query. Hey, who matters to me, right? Then it advertises itself, which is the key. Okay, which means that, hey, I mean this is my general meaning, and then a value. So key and value can be, think of it like if you have a book, right? So the key can be the index of the book, right? Where I just give a one-liner that I am just this. But value is like a whole description of me, that what is I bring to the table, my whole content. So every word translates, becomes into this query, key, value. Okay, we transform each word's vector into three different versions, one for each job. So if my example is the cat sat on a mat, I will take each word, okay, and translate them into three different vectors: query, key, value. Okay, now the cat's query will be what. So if I take the vector of cat, right? So what will its query look like? It will look like this. In English, it will look like this: what action am I doing? Where am I? So I have taken the vector of cat and converted into a query which says what action am I doing and where am I. I take the vector of cat and convert it into a key. I am a living animal. I perform actions. I take the vector of cat and convert it into a value which says I am a small furry pet, four-legged mammal, independent creature, mouse chaser, household companion, right? So like I said, for each and every word, right, I will transform them into query, key, and value. Now what I will do is, like, even before going into that, think of it like you are in a room filled with like 5 to 7 people, right? And you want to understand what every person is doing in the room. What will you do? You will go in and talk to different people. And what you will do is you will say that, hey, my query is, I want to understand what am I doing in this sentence. So that is my query. My key is, hey, I can do this. Okay, so if you have to understand I am relevant to you, you can take my key and understand how am I relevant to you. And value is, finally, if you think that my key can be important to you in understanding your meaning, then you can multiply me by your value. Okay, something like that. This is the overall like understanding. Think of these words as like persons in the room who are trying to understand their meaning in this particular room. Okay. So now what happens is, like I said, right, we'll take each word and transform them into query, key, and value matrices. How do we do that? We take the vector of cat and multiply it by a matrix called WQ, which is the query matrix, multiplied with WK, which is the key matrix, and WV, which is the value matrix. Okay. Now, just for you to visualize, these three matrices are same for every word. And for all these three words, for each word, we'll multiply them with by WQ, WK, WV. Okay. So think of it like WQ could be something like this, WK will be something like this, WV will be something like this. Like I said, right, these matrices will not be exactly like this four-dimensional things. It will be again 4096 dimensions, but I'm just making this as small, represented them as small so that we can understand. And these are also learned during training. Like I told, right, during the training phase, we learn certain parameters. So think of WQ, WK, and WV as certain parameters in our system. We take every word and convert it into a query, convert it into a key, and convert it into a value. Okay. Now what happens is, now let's see. Okay. Now what will happen? So if I take the vector of cat, okay. So what we will do is, like, let's say the vector of cat was 0, 2, 0, 2, like we took over here, right? See 0, 2, 0, 2. Okay. So I'll take the vector of cat and I'll take the initial vector of cat, multiply it by this matrix WQ, and I will get a result as this 0, 4, 2, 2. So what happened to the vector of cat? Now see, so these are numbers at a surface level, but their English meaning has changed. Okay. Initially cat was just, I am an animal. Now the cat's question becomes, because this is the query vector, it became what action am I doing? Okay. So this vector will move towards what action am I doing? Okay. Similarly, I will take the vector of cat and multiply it by the key vector. Okay. So in the terms of vector representation, the key vector of cat will become something like this. But what does it mean in English? Cat's label, I am a living animal. Okay. Every word has query, key, and value, right? So how do we form these vectors is what I'm explaining. I take the initial vector, I multiply by this matrix, I get this. I take the initial vector, multiply it by this matrix, I get this. I take the initial vector of this, multiply it with the value vector, and I get this. And what is the value? Cat's actual content. I am a small furry pet, four-legged mammal. Okay. Now imagine cat has transformed itself into a question, into a key, and into a value. Okay. Similarly, how SAT will do in this sentence is again the same thing. I have the initial SAT vector, I'll multiply by WQ. But the question of the SAT vector will transform like this. It will start asking this question: who is doing the sitting, right? I know SAT means the action of sitting, but who is doing the sitting, right? Similarly, for the value vector 1, 1, 1 into the key vector, I will multiply, which is like this, and I will get this vector 2, 2, 2. What does it mean? SAT's label or the SAT's key vector, what does it mean? I usually need a subject who is sitting and often a location. So it will multiply itself. And the vector representation, this will mean this. Okay. Similarly, I'll have this, and the value vector will something become like this. The value vector means this in English. SAT's actual content, the act of lowering one body onto a surface. So SAT also transformed it into a query. Hey, who is sitting on me? Okay. Into a key. I know that I usually need a subject. Okay. And the value that sitting SAT actually means lowering down one's body onto a surface. So mathematically, what happened? We had these vectors. They got transformed into query vector. See, the vector of the got transformed, the vector of cat got transformed, the vector of SAT got transformed into these new vectors. Okay, these are the query vectors. Similarly, the vector of the got transformed into key vector, the vector of cat transformed into the key vector, and then value similarly. So three new matrices we got after this. Okay. After this key query, key, value. And like I said, it will happen for every word in the sentence. Okay. Now let's say what I have. So let's take a step back. Till this step, what was attention? What did we say? That during attention, I want to look at the surrounding context to understand what's going on. Okay. So the cat sat on mat, right? So over here, if I just, after vectorization, I just have the meaning cat, I am an animal. But what am I doing in this context, right? Cat has a question that what am I doing? What action am I performing? So what can answer that? Sat and mat, right? Because the cat is performing the action of sitting on a mat. So these vectors have the answer, right? So I translated my vector of cat into query, key, and value. Similarly, sat just knows that sitting, hey, I mean sitting, who is sitting on me in this particular sentence. whether it's a cat, who is actually doing the sitting action. In this sentence, cat is doing the sitting action, and where is it happening? On the mat, right? Similarly, mat has this question, right? So till now, we have just taken each word and translated and turned them into questions and keys. Okay. Now, let's say SAT is doing the attention. Okay. So what SAT will do is SAT picks up its query vector, which is QSAT, for example, which was the initial vector 222, like we said, and it is asking the question, who did this sitting, right? So in order to find who is doing the sitting, what I will do is compare SAT's query against every word's key. Okay. Comparison is done via dot product. Like I explained, dot product in a vector space can give how close or how similar are the meanings, right? So that's just multiply each pair of numbers, then add them all up. It measures how aligned two numbers are. High, if the numbers are high, they are aligned and relevant, right? So what I'm doing over here, the word SAT is doing the attention, which is looking around to understand its meaning. So my query, the query vector of SAT is who is doing the sitting. So what basically I will do is take the query vector of SAT, multiply it with the key of multiply it with the key of cat, multiply it with the key of SAT. Okay. What will happen over here? By doing this multiplication, I will understand which word is more relevant to me. Because how? Because I will do a dot product. Okay. So I'll take this vector of SAT, multiply it with this key of I'll take the query of SAT, multiply it with key of cat. I will take the query vector of SAT, multiply it with the key vector of SAT. Okay, itself. Okay. Since I said we'll do this with all the words in our sentence, right? So now if we do this if I do this multiplication, I'll get a number 8. If I do this multiplication, this vector multiplication, I'll get the number 16 with cat. When I do this multiplication, query of SAT with key of SAT, I'll get this number 16. So we'll get the relevance score. My query was who is doing the setting. I can see the is contributing less, cat is contributing more, and SAT with itself is also contributing like 16 points only. Okay, cat and SAT both score high. The scores lower. Okay, this is low. Cat and SAT are scoring high. Okay. Now what we do is, see, after this sentence, did I get my answer? Can the vector of SAT get enhanced? Because I know I multiplied it with the key vectors of the cat and SAT, and I see that the cat's relevance is higher. So I now am getting the answer that the cat is maybe sitting on me. Okay. So we got the relevance score. Now we do some more mathematical operations. So in our, like I said, right, in GPT and all, there are 496 dimensions. Okay. Which means that these numbers are not just 4222s, but 4096 kind of numbers. Okay. So when you get these scores, right, this can be very big scores, right, which the computers cannot handle in floating point numbers or numbers. So we do some normalization over here. Think of this part. Okay. We just do some normalization over here. The scores will be the same. The relevance will be the same, but I just don't want this as numbers. I want this as percentages. Okay. So I will do some operations, which is I will take my scores and divide it by the root square of dimensions. Okay. So my dimensions is 4. Root square of 4 is 2. So I will take this score 8 divided by 2, 4. I will take the score 16 divided by 2, it becomes 8. I will take this score 16 and divided by 2, which becomes 8. Now, like I said, right, I want still the answer in percentage. So I will do some exponential operation. So this is not very important, but since this is a part of the formula, I'm just explaining it. So what it generally means is I want the answer in percentage that to my question, who is doing the sitting, right? Since I said that SAT is now doing the attention work. So I want an answer whether who is contributing more to me. And I want that answer in percentage. I figured out that by matrix multiplication, I these scores, but I want to convert it into a percentage. Okay. So I do some exponential operation over here. I take an exponent and multiply it by 4, so it becomes this. And then I divide it by this sum. So I will get this percentages now, which means the is contributing 1%, cat is contributing 49, SAT is contributing 49. So since I did the attention of SAT via SAT, so SAT into SAT. So since I'm doing it with myself, this does not answers my question a lot because this is me myself over here, right? Cat is the major thing which can affect my score, right? So this tells us cat is very relevant to SAT. This is the is barely relevant because it's 1% coming to, and SAT itself is keeping half of its information because we are multiplying SAT by itself. So I think we should remove it, right? Cat is the thing which is doing the action over here. Okay. So just to explain, so we had SAT, right? We are trying to identify what is it doing in this sentence, right? There can be another sentence like the man sat on wall. Okay. So sat's general meaning is like sitting, but in this sentence it means difference. The cat sat on a wall. The cat sat on mat, right? Here the meaning of sat is different. So attention looks at what is happening. So after this is how we calculated the attention score. The cat is affecting me the most. Okay. So now what we will do is I know that the is impacting me 1%, cat is impacting me by 49%, sat is by 49%. So what I will do is I will take these values, like 1% was there, right? So I'll take 0.01, cat was 49%, 0.49, and 0.49 for sat as well. Now I will take the value vector of the value vector of cat and value vector of sat and multiply them. Now the final vector of sat will become something like this. What does it mean? The new vector of sat after attention, the old vector was, let's say, 111. The new one is 1 point this thing. The vector got nudged, right? It moved towards cat, towards the vector cat, which means because it was impacting. So now sat gets its answer. Hey, who is doing the sitting action on me? It can figure out, hey, cat is doing the sitting action on me. So this is how attention.
Yeah, sorry, Ankit, sorry to interrupt.
Yeah, go ahead.
Now it is trying to evaluate the answer based on the trained model, right? And before asking the question, where is the cat sitting? User might have given a paragraph where he mentioned the cat sat on table itself. Then will it consider the user provided input, or it will consider the trained input?
No. Okay. So what happens during training is, okay, there are two questions. So you are saying that, let's say, during the training, it learned the cat sat on a mat, right?
Yeah.
And now during inference, what is happening is the user gave some other context at the beginning and then gave the sentence the cat sat on a mat. Okay. So what it does, like it will consider the user words, like based on the training, it can understand the cat sat on a mat, but it will take the previous context that the user has done and it will do the attention mechanism over with that also. Like in our previous question, like I said, right? So in this example, I am taking just a very simple sentence, but everything on your input is considered while giving you an answer. So when attention happens on that, it will grab the context from the previous sentences also. It's not like it will just take one sentence. Okay, I think Swati, what you are getting confused is like if I have some paragraph, right? Paragraph, right? That has some context, and then I'm doing the attention on this line. Okay, then will it take the context of just this? No. It will take the context of the entire thing, whatever you have pasted in, right? It will consider all the things, like from end to end. Like if your paragraph is 1 to 100, it will consider all the words, and if sat is at 50th position, it will consider everything between 1 to 100 to so that it can accurately predict what am I doing or who is doing the sitting action.
Yeah, so it is considering the input in this case.
Yeah.
And can we also can we also provide, can we ask it to choose the best answer?
Yeah. It can, like, let's say if there are multiple sitting actions in your whole paragraph, right? So you can ask it contextual questions. Maybe, see, don't relate. See, this was, I mean, kind of a weird example I took because it's easy to explain what kind of transformation is happening over here, right? But in real world, like I took my previous example, right? You generally go in, you can ask different things, but you generally go, as software developers, we take in code and we ask some questions, right? So it's a general workflow. So I showed, right, it will take the whole code context and answer you based on that. It will develop layer by layer an understanding of what the code is doing, what is the bug, and how to answer that. Okay. Sure.
Yeah, thank you.
Yeah, no problem. I think it was a good question so that everybody understands. So basically, nothing is happening like how, as humans, right? If I have to understand a sentence, I look at everything, right? So let me take one easier. I mean, how do we understand? Okay. So if I type in the word, don't look at the word altogether. Okay. The cat sat on a mat. Now, don't look at the word altogether. How your mind perceived it is, first it saw cat, then it saw sitting, then it saw mat, then it connected all the three concepts together, right? There is some cat. Okay. There is some mat and there is some sitting action. Cat is doing the sitting action of sitting on a mat. So your mind picturized this, right? But your mind, I mean, right now, if you look at the sentence in one go, you know your mind has been trained so much that you know this much. But if you break it down slowly, right, this is how you have picturized it. The cat, the sat, sitting action, and the mat. Same thing is happening in attention over here. We are looking at different parts of the sentence. How are they contributing to my meaning is what we are trying to do. The same, like initially I told, right? Neural networks are mimic the human brain, right? So neural networks are doing a bunch of mathematical actions, same to what humans do in order to understand the meaning of the sentence. But how logically it is achieved via maths is what I was trying to show over here. I hope it